Hi everybody. So here we go. Pre-lecture 6 is on separation of variables. So at this point, I'm hoping that you know what a partial differential equation looks like, and that's what we talked about last time. It's sort of like an ordinary differential equation, but it's for a function of two variables, or three or four. So if you have a function which depends on both x and t, and you have an equation which has that function in it and its derivatives, and its partial derivatives because it has multiple variables, you have a partial differential equation. And we talked about kind of classifying those last time and sort of what they look like and how the solutions can be a lot more complicated. But now it's time to actually start thinking about how do we solve these things. So let's get down to it and try to figure out how to actually attack these partial differential equations and try to solve them. Okay, so we know suppose you've got some kind of PDE for a function y is a function of x and t. So let's say, suppose you have a PDE for the function y, which is a function of two variables, x and t. Okay? And for now, I'm going to be totally general, and I'm going to assume that you also have the relevant number of boundary conditions and initial conditions. Okay? How do you actually go about solving a partial differential equation? Well, it's a really complicated subject. I mean, the problem is they're really difficult to solve, most of them. So you could spend a whole class or your whole life trying to figure out how to solve certain partial differential equations. But I'm going to give you your first line of defense, or I guess your first line of offense, if you're going to start kind of attacking these things. And the first technique that you learn is something called separation of variables. So your first technique is called separation of variables. And it's not the same separation of variables that you saw in PCS 521. You know, for example, if you have an ODE that looks like, I think we did this one last time, dz dt is equal to minus z. We did a separation of variables there, which was like dz over z. Get all the z's on one side and get the t on one side and then do an integral. But that's not this kind. That's the separation of variables in ordinary differential equations. The separation of variables in PDEs looks a little different. So here's the idea. You assume, or you guess, a form of the solution which looks like this. Y of x and t is equal to the product of two functions, capital X, which depends only on x, times capital T, which depends only on t. So in other words, you guess that the x dependence is sort of factorizable from the t dependence. And you're going to say, well, how do you know to guess that? And it's because a bunch of people a long time ago tried a bunch of things, and this kind of worked sometimes. So, you know, you've probably learned, I hope you've learned by this time, that solving differential equations is more of like a bunch of guessing. Like, it's just you've learned what the right thing to guess is after a while because people have guessed it before and they figured out it worked. So this is one that works sometimes. So why would you do this? Why? Because it works sometimes. Not all the time. But if you don't know what to do and you have a PDE, you can try this. Try and separate the variables. And then you plug it into the PDE, and then hopefully, if everything works, you'll end up with two ordinary differential equations instead of one partial differential equation. So this is what you're kind of hoping for, is that you're hoping that you can reduce your partial differential equation into two ordinary differential equations. And if you can get it into ordinary differential equations, then you're in paradise because you know pretty well how to solve ordinary differential equations. Just the partial differential equations are harder. So the best way to show this is with an example. And so I will start working on an example here. And it's based on one of the examples from the book by Herman, 5.4. And let me describe this example for you. So imagine you have this system. You have a long pipe, okay? And the pipe, let's say it is length L. So this is length L. And the pipe is filled with like a solution, a liquid solution. And we're going to say that the solution, I'm just going to represent it like this. It has some salt dissolved in it. So it's salt solution in here, okay? And maybe in certain places, like maybe here on this, at this point here, I've got a lot of salt. So it's very salty here to start. And then maybe here it's not as salty. And then maybe over here there's a lot of salt. So you have some kind of clumping of the salt solution, or you have some concentration of salt distributed throughout this pipe. And then you take the pipe and you put it in contact with two large containers of pure water, H2O. So on the border, or on the boundary here, you have to imagine really, really giant, I just can't draw it to scale, giant containers of water. So this is pure water on the left side and the right side. And then the pipe in the middle has some solution in it. And you want to know what happens to that salty solution as time goes on. So to go a little bit further, let's denote this C of x and t. This here is going to be x equals to 0. This here is going to be x equals to L. And I guess this will be my positive x-axis. C of x and t is going to be the concentration of salt in the solution at position x at time t. Okay. So C of x and t is my function of two variables that tells me what is the concentration of salt at some distance along this pipe at some time t. If you don't like salt, if you're you're a medical physicist and you want to think about, I don't want to deal with salt, I want to deal with drugs diffusing in the body, and then you can replace the salt with some sort of dye which diffuses, or some kind of drug. Same idea, right? It's the diffusion of some concentration. Modeling that with this system. Notice there's only one variable, which is x. So I'm gonna ignore the kind of small distance of the pipe this way. I'm not gonna worry about how the molecules diffuse up and down. I only am gonna worry about how they diffuse left and right. Okay. Of course, you can do it in 3 dimensions. It just gets more complicated. Okay, this obeys an equation. Here's the PDE that describes this. It's called, unsurprisingly, the diffusion equation, because hopefully you guys know from your medical physics career and maybe from other courses that things diffuse from high concentration to low concentration. So I've got salty solution in the middle there. There's going to be a diffusion of the salt solution outwards from the areas of high concentration to low concentration. And this diffusion equation looks like this. Partial derivative with respect to t of c of x and t is equal to some constant, big D, times the second derivative with respect to x of c and x and t. Or if you want to write it more compactly, c dot of x and t, remember the dot means derivative with respect to time, is equal to d times c double prime of x and t. So the dot means derivative with respect to time, the prime means derivative with respect to x. This d here is a constant, which is called the diffusion coefficient. Which is just describes how easily the molecules diffuse. It's just a constant. Okay. This equation might look familiar to you because I made you guys watch a video about the heat equation. And so let me just take a side note here. The heat equation, which was the equation that Fourier was trying to solve when he came up with Fourier series and Fourier analysis. That was the way that heat spreads out from a rod, right? So you have a rod which has some temperature distribution, and you want to know what temperature is it at different points along the rod as time goes on. The heat equation looks like this: dt for the temperature T of x and t along the rod is equal to some constant k times d squared t dx squared of x and t. And you'll notice that looks exactly the same as the diffusion equation. This k is a constant which is called the thermal conductivity. Or if you write this equation, it looks, in the shorthand, it looks like this: T dot of x and t is equal to k times T double prime of x and t. So these look almost identical, just with different letters. So it looks the same as the diffusion equation. And that's something that's really, I think, quite fascinating, that the mathematics describing heat flow also describe diffusion. So if you can solve this diffusion equation, you can also say how heat spreads through a rod. And if you can solve how heat spreads out in a two-dimensional plate, you can also describe how concentration of dye spreads out in a two-dimensional plate, right? Or in a two-dimensional tank of water. Anyway, so that's a bit of a side note, and trying to, I guess, motivate that what I'm discussing here is actually has broad applicability in many systems of physics. It's not just, I'm not just talking about salt solution in a pipe. I'm also talking about the diffusion of dye throughout the body. I'm talking about the flow of heat in a rod, and so on. Okay, so back to our PDE, which is let's do the diffusion equation here. So now apply our separation of variables. So back to the diffusion equation. Try to separate variables. So my PDE was C dot is equal to some constant D times C double prime. So I will guess C of x and t has a factorized form, capitalized X, or capital X, which is a function of x, and t is a function of time. It's just kind of the convention that we always call the function the capital letter and the variable the small letter. That t there doesn't necessarily mean temperature, it's just the name of some function which depends on t. Okay. And then plug it into the PDE. So what do I have? C dot. Well, take the derivative with respect to time. That's dt of x, which depends on x, and t, which depends on t. But if it's a partial derivative, the x can be treated as a constant, so the x comes out front. And I have d by dt of t, which, let me just write it like this, x times, let me keep the variables in there, x of x times t dot of t. And then c double prime, that's the second derivative, partial derivative, x of x, t of t. Now when I'm taking the partial derivative with respect to x, the t can be treated as a constant, so t is a function of t, d squared dx squared times x of x, which is t of t times x double prime of x. Okay, plug into the PDE. My PDE tells me c dot is equal to d times c double prime. C dot is equal to some constant times c double prime. And that means that x of x times t dot of t is equal to d times t of t times x double prime of x. Okay. At this point, normally what you do is you try to get all of the x's on one side and all of the t's on the other. So that's going to be our goal. Now move all x dependence to one side. So the way to do that usually is you divide by both x, big X, and big T. So what I'm going to do is I'm going to divide both sides by x of x, t of t. And same thing on this side, x of x, t of t. Okay. It's just a fast way to get everything on one side. And what happens? The left side, there's an x on the top and an x on the bottom. On the right side, there's a t on the top and a t on the bottom. And I'm left with the following thing. T dot of t over capital T is equal to d times x double prime of x divided by x. Okay. So this doesn't seem so useful so far. But once you've got it in this form, where you can get all of the t dependence on one side and all of the x dependence on the other side, you can make a really crucial argument. So here comes the argument. And this is the one that, for me, it took me quite a while to understand this argument. So here comes the argument. Take a look at the right-hand side. This thing here. By assumption, the right-hand side cannot depend on t. On time. That was the whole point, right? We assumed that the capital X didn't depend on time, it only depended on the spatial variable, small x. So we assumed that to start. So we're going to say that the capital X doesn't depend on time at all, and so that means the right-hand side doesn't depend on time. But here comes a puzzling thing, is that it cannot depend on x either. But the right-hand side can't depend on x either. Why is that? Because the left-hand side is equal to the right-hand side. And the left-hand side doesn't depend on x. Right? So by assumption, we assume the thing on the left doesn't depend on x. And if those two things are equal, if the thing on the left doesn't depend on x, the thing on the right doesn't depend on x. So therefore, neither of those sides depends on x or t. What does this mean? The only way that's possible is if they are each a constant. Okay. So go through it one more time. The right-hand side doesn't depend on t by assumption, but it also can't depend on x because it has to equal to the left-hand side, and the left-hand side doesn't depend on x. So the right-hand side can't depend on x or t. And the only way out of this is that it's equal to a constant. Only way out is the right-hand side is equal to a constant. And that means that the left-hand side is equal to the same constant. So this argument is quite important, that whenever you are able to separate your PDE into like getting all of the dependence of one variable on one side and all of the dependence on the other side, it means that both of those sides is equal to a constant and equal to the same constant. And we're going to call that constant lambda. Just going to make up a name for it, lambda. So that means that I've gone from my PDE into two equations. I have the left-hand side is t dot of t over t of t must be equal to a constant, which I'm going to call lambda. And the right-hand side looks like this. It looks like d x double prime over x, d x double prime of x over big X of x is equal to the same constant lambda. Okay. And what do I have here? I have now two ODEs. This is an ODE, and this is an ODE. So I have ODE number 1 and ODE number 2. And those ODEs are related in the sense that they're both equal to the same constant. So there's a connection between those two, which is given by that constant. But I have now I can go back to PCS 521 or back to your courses from last semester, and I can use the techniques for ODEs to solve these. And now that PDE doesn't look so bad, right? So I can use my techniques for ODEs. To solve. Okay. Let me try to summarize the main thrust of this pre-lecture. You have a PDE, you don't know what to do with it. The first thing you do is you try to guess something where the two variables factorize from each other. So you guess that it's the product of one function, which depends on one of the variables, times the other function, which depends on the other variable. Plug that into the PDE, and then usually you divide by the product of the x and the t, or you divide by the whole function that you originally guessed. And you're able to separate the x dependence on one side of the equation from the t dependence on the other side. And whenever you're able to do that, it means that both of those sides are equal to a constant, equal to the same constant. And by that method, you reduce your PDE into a couple of ODEs, which you then can solve. So we'll pick it up here, and now we'll start thinking about what are the solutions of those ODEs, and then how do we, from there, construct the most general solution to our PDE. So I hope that you've enjoyed this lecture or found it useful, and thanks for your attention.